All right, good morning everybody. Happy Friday. So, isang araw na lang mag-weekend na and we can get all our rest. So, today will hopefully at dapat matapos na natin yung module number 2. It's a week overdue. Pero let's just have a quick recap of what we did so far. So basically, ang ginawa pa lang natin in module number 2, we look at a numerical way. Actually, hindi nga numerical eh. Tinignan natin paano bumuo ng isang algebraic interpolating polynomial. This is a polynomial that approximates the behavior of either a given set of data or a given function, right? In such a way that it will pass through all the given data points in our particular problem. And that's what sets interpolation apart from other approximation techniques. And we ask the help of MATLAB para ibigay sa atin yung interpolating polynomial. Key takeaways, kapag ka meron kang n+1 data points, your polynomial, your algebraic interpolating polynomial will be unique and it is of degree at most n. Right? So tiningnan din natin na ang laking bagay nung meron tayong isang function na nakakapag-approximate sa isang given set of data because after we get this polynomial model, we can apply to it the different tools that we learned from analysis. Yun yung ginawa natin last time na kaya pala natin kunin yung optimal value say ng isang yung optimal selling price for a certain product given only the a set of price and demand data, right? Ka ng data, kaya na natin siyang, or pag meron ka ng model, kaya na nating i-apply yung mga Math 30 series tools na natutunan natin before. And what else? And at ang kagandahan ng paggamit natin ng algebraic interpolating polynomial or in fact these are polynomials ay kasi ang dali nilang i-manipulate. Ang derivative nila ay polynomial pa rin, ang integral nila ay polynomial pa rin. So, but one thing that we have, or the only thing that we have seen so far is the utility of this procedure when you are given a discrete set of data. Pero hindi lang ganun yung gamit ng algebraic interpolating polynomial. And sometimes, meron kasing mga functions na hirap i-manipulate, all right, on their own, in the sense of calculus or in the sense of even simple algebra, no? Pero napakahirap nilang i-manipulate or gamitin sa isang operation on their own, kaya ang pwede natin gawin ay palitan sila ng mas simpleng function. Right? For instance, we have example 2.6 here in the module, wherein we are dealing with a very simple function, the function e to the x squared. Right? Now, what can we say about the function e to the x squared? It's a very basic function. Wala nga kakomplikasyon yung pagkaka-define sa function. You get a number x, you get x squared easily, and then you use that exponent to e, makukuha mo yung value ni e to the x squared. So there's no big fuss about finding e to the x squared or evaluating its value. Also, e to the x squared is continuous. So, di ba alam natin sa Math 30 series, kapag alam natin ng isang function ay continuous, this is more of this has nice properties, right? It's the class of well-behaved functions in some sense, right? So continuous e to the x squared, and not just that, e to the x squared and all of its derivatives are also continuous. So e to the x squared is continuously smooth, right? Kasi lahat ng derivatives niya ay continuous din. So napakaganda ng properties ni e to the x squared. Kaya lang, pag pina-integrate sa atin yung e to the x squared, we cannot do anything because e to the x squared doesn't have a closed form antiderivative. Okay? So isipin mo, simpleng-simple yung e to the x squared, dapat maling-mali yung pag-i-integrate nan. But kahit anong technique of integration, kahit integration by parts, algebraic substitution, ano pa ba mga natutunan yung integration techniques? Trigonometric sub, and all of those things, they will fail because e to the x squared simply doesn't have any closed form antiderivative. Okay? Tapos, kung hindi pala natin siya makukunan ng closed form antiderivative, okay? Paano natin ngayon i-evaluate yung say definite integral ni e to the x squared dx from 0 to 1/2, right? So hindi natin magagamit yung first fundamental theorem of calculus. Alright? Kasi nga wala tayong makukuha ang antiderivative para kay e to the x squared. And this is simply mind-boggling kasi ang simple nung e to the x squared and yet wala tayong magagawa kasi nga yung function na to ay merong mga theoretical limitations. Okay? So, at this particular point, we can tap yung natutunan natin about interpolation. So, I will not try to integrate this by hand because wala nga ang solution yon. So, ang gagawin ko ngayon, si e to the x squared, papalitan ko by a function that mimics its behavior. Iisip ako ng isang function na mag-approximate sa e to the x squared, at least sa interval 0 to 1/2, tapos pag nakakuha na ako ng approximating function na yon, siya yung i-integrate ko. And whatever that value is, that would be my approximate for the integral of e to the x squared from 0 to 1/2. But again, there, I will be hoping na kapag ka maganda yung approximation para kay e to the x squared by whatever function I choose, sana ma-carry over yung approximation ng integral. Dapat, kung malapit yung makukuha kong approximant kay e to the x squared, sana yung integral ng approximating function na yon ay malapit dito sa gusto nating value ng integral. Right? Of course, later today, we will discuss the errors involved in interpolation. Pero tingnan natin, what will happen if I'll use an algebraic interpolating polynomial as the basis for calculating or approximating the integral of e to the x squared dx from 0 to 1/2. Okay? So ito yung isang aspect ng interpolation. Pwedeng given ka ng isang function. Napaka-komplikado nga lang ng function na yon, or there are some technical issues with said function, kaya hindi natin siya pwedeng gamitin directly doon sa ating computations. In this particular case, our computation is for the definite integral, right? So ganun gagawin ko. And for instance here, I choose to say okay. May sinabi siyang requirement, dapat daw gumamit tayo ng degree 8 interpolating polynomial na pang-approximate kay e to the x squared, and then instead of integrating e to the x squared, we integrate that degree 8 interpolating polynomial, right? But we have learned earlier na kapag ka meron kang n plus 1 points, magkakaroon ka ng polynomial of degree at most n. Now, we want a polynomial of degree exactly equal to 8. So, para ma-solve itong problem na to, kailangan ko siguro ng at least 9 points. So, doon ako magsisimula. I'll get 9 points, pero dapat ranging from 0 to 1/2 because, again, as I mentioned as a spoiler last time, ang goodness of fit o ang kagandahan ng approximation using an algebraic interpolating polynomial is only guaranteed from the smallest abscissa to the largest abscissa. Since we want to get a good approximation for e to the x squared over the interval of integration, okay? So pipiliin ko ngayon, pipili ako ng at least 9 points for the or exactly 9 points for my first pass, right? Tapos yung siyam na points na yon, sisiguraduhin ko nasa loob ng interval 0 to 1/2. And I will arbitrarily choose to use 9 equally spaced abscissas starting from 0 until 1/2. All right? So ito yung makukuha ko. Pupili ako ng siyam na points mula kay siyam nga ba ito? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 points, equally spaced, ranging from 0 to 1/2. And then I'll get e to the x squared. Now, I get this data. All right? Pag nakuha ko na yung data na yan, kukunin ko ngayon yung algebraic interpolating polynomial. And what you just need to do is plug this values into your MATLAB code. All right? Ito yung gagawin nating t. Tapos ito yung gagawin nating data. All right? Ito yung d dun sa ating sinulat na code. You can easily compute this using MATLAB right away. So kapag sinet mo na si t to be this vector, okay? Tapos lalagyan mo lang yun ng semicolon, ano? So yun na yung t. Para ma-compute si d, pwede mo nang gawin ay d equals exp. Exp is e raised to something, right? So yun yung syntax para sa e raised to something. Tapos yung exponent ni e siya yung nasa loob ng parentheses. And then, ang exponent ni e ay x squared. So, ibig sabihin, gagamitin ko yung mga t values. So, t, kaya lang naka-square sila. Pero si t ay vector, so dapat t dot caret 2. Ito yung gagamitin nyo para ma-compute yung e to the x squared. Kasi, kapag ka merong, di ba, by default, ang thinking ni MATLAB, ang input mo lagi ay vector. Alright? So, pag ginawa mong t squared, tapos si t ay vector, ang gagawin ni MATLAB, titingnan niya to as vector t times vector t. And depende dun sa size ni t, this might be undefined. Kasi ititreat niya si t as a matrix, so pag multiply niya si t by yung sarili niya. Pero dahil si t natin ay vector, it would be a 9 by 1 vector. Pag minultiply mo siya ng 9 by 1 vector, magrereklamo si MATLAB. Kasi hindi nagmamatch yung dimensions. Hindi defined ang multiplication ng isang 9 by 1 vector by another 9 by 1 vector. So yun yung gagawin ni MATLAB pag ginawa mo lang t raised to the 2. Pero essentially, ang gusto ko lang naman, yung mga x values, ini-square natin sila. So kapag ka meron kang vector of x values, tas gusto mong component-wise squaring, alright, kailangan mo lagyan ng dot, tapos yung operation, raised to the second power. So yung dot na to, ito yung nagsasabi na component-wise, MATLAB yung gawin mong operation. Okay, so pag tinype nyo itong t dot caret 2, ang ibibigay nito ay 0 squared, vector na 0 squared, 0.0625 squared, all the way up to 0.5 squared. Tapos magkakaroon ka ng vector na yan. Alright? So, eto na yung i-input mo dun sa exponential. Alright? So, okay lang naman yung exponential kapag ka meron kang exponential ng vector, o exponential ng vector, ibibigay nitong laman ay e to the first entry ng vector, second entry ng vector, e raised to the third entry of the vector, all the way up to the last component. Okay? So, ganun mo siya ipapakompute kay MATLAB ng diretso. Right? So, once you have your T, once you have your D, right? So, kaya mo na itong ipagawa kay MATLAB, right? Actually, pwede ko palang i-demo, no? Ito yung polynomial na makukuha natin. Yung interpolating polynomial. And luckily, using this 9 points, we get exactly a degree 8 polynomial as required in the problem. Kung kamalas-malasan, may mga nag-cancel dito, tapos degree 7 lang to, then you need to add 1 more point to get a degree 8 polynomial. Okay? But luckily, degree 8 polynomial na to, then ito yung i-integrate natin instead na si e to the x squared. Oh, I forgot the dx here. Okay, so we say that the integral of e to the x squared dx is approximately equal to the integral of the degree 8 AIP. And then anong value nito? Ito raw yan, 0.544987. Okay? Now, how good is this? Now, of course, kung malapit si p of si p sub 8 kay e to the x squared, it doesn't automatically follow that the integrals will also be very close to each other. Medyo may posibleng magkaiba ng order yung dalawang integrals, right? Or posible silang magkaroon ng magkaibang relative error, right? Pero ideally, kasi nga ang integration ay isang continuous operator, kapag ka malapit yung integrands sa isa't isa, most of the times or almost always, yung integrals ay malapit din sa isa't isa. Now, I used maximum precision kay Mathematica para i-approximate etong e to the x squared dx, and the best approximate Mathematica can give me is this guy. Tapos kinompute ko yung absolute error. So kinompute ko gaano kalayo etong itong nakuha ko mula sa pag-integrate ng algebraic interpolating polynomial doon sa best known approximate para kay integral ng e to the x squared. And the relative difference is 2.94 times 10 to the negative 11. And this is very, very small, right? Virtually zero na to. Malapit na siya nga sa machine precision na 10 to the minus 16. So essentially here, the degree 8 interpolating polynomial gave us a very good estimate for the integral of e to the x squared. Okay? Siguro we have enough time. Hindi ko na papangarapin na tapusin yung or simulan yung module number 3 today. So maybe we can spend a little time na ipakita kung paano ito gagawin kay MATLAB. Alright? Para rin ma-practice kayo paggamit kay MATLAB, kung nagta-transition kayo into MATLAB. So pasensya na lang dun sa mga ayaw mag-transition kay MATLAB, bias ko talaga si MATLAB, so kaya MATLAB yung ginagamit ko sa demo. Alright? So hopefully, maging masanay na tayo sa MATLAB, or kung ayaw niyo talaga, sige, mag-Python kayo forever, hindi ko nga lang siya gagamitin sa klase, Hold on, guys. Umatake na naman yung kalaban ko tuwing nagkaklase, yung runny nose. Sorry about that. So sometimes I'll mute myself to sneeze or something. All right. So okay. So let me stop sharing my PDF and share my MATLAB screen so that we can play more with it. Okay. Okay. So implement natin, i-recreate natin yung example. And this is nice. This is one nice way to check the code that you have written for, say, the laboratory exercise. I-recreate nyo yung mga examples dun sa modules. And hopefully, you can get those data. Then you'll be more confident that your code is working well as expected, para mas confident kayo dun sa LabXer. Speaking of LabXer, pinag-isipan ko pa rin hanggang kanina pagkagising ko, ano kaya yung papa-LabXer natin on Monday? Parang wala pa akong naituro na bago. Dapat nasa module 3 na yung exercise on Monday. But let me think about it, and because of that, medyo malilate. Okay lang ba? Malilate ng konti. Yung pag-upload ko ng LabXer, maybe wait until right before midnight tonight. Okay? Pero maiksi lang siya. Siguro one item about error. Okay, na i-discuss natin in the second half of today's meeting. So super maiksi lang siya. Siguro kaya niyong gawin siya in 30 minutes. So, or more, right? Pero at least 30 minutes on Monday. So I hope that's okay. So tingnan natin. So remember, ang lines 8 and 9. So para dun sa problem 2.6 or example 2.6, maglalagay ako ng saka bagong vector D. Okay lang ba yung size size ng screen? Nakikita niyo pa rin ba yung text, or do you want me to make it bigger? Okay na? All right, good. So si T. So si T ay from 0 to 0.5, kailangan natin ng siyam na points. So one way to generate it is to use the linspace command. Kasi there are sometimes there are more than one way to do something in MATLAB. So para kumuha ng isang vector of equally spaced points kay MATLAB, pwede natin gamitin yung linspace na command. Okay? So linspace na command, linspace, ito yung command. Lagay nyo lang yung sa linspace nga ba? Ano kailangan ko? Yung starting number, siya yung unang input. So we start at 0. And then we want to end at 0.5. Tapos ilang points yung gusto ko, yun yung third argument. So common 9. So this syntax here will give us a set of 9 points, the third parameter. So siyam na points na equally spaced mula kay 0 hanggang 0.5. Right? So if I want to see what happens here, I can just highlight the line that I want to run. Gusto ko lang makita kung tama nga ba itong syntax ito. Then I'll press F9, and there we go. I get a vector starting from 0 hanggang 0.5 na may siyam na equally spaced points. And this is exactly what we have in the module, right? So siya si T. Siyam na columns. Okay, good. So this is 1 by 9. All right. And then sabi ko kanina, kailangan din natin yung data D. Alright? Ito yung mga function value kay e to the x squared nung mga elements ni T, nung mga abscissas natin. So here, I'll have exp of, remember, this guy will do e raised to whatever's inside the parentheses. And then, nasa loob niya dapat ay yung component twice squares. So dito, ilalagay ko ay T Pero gusto ko i-square muna bawat isang element ni t. So what I'll do is t dot caret 2. Alright? Pwede nating tingnan, ano yung mangyayari, sir, pagka hindi ko nilagay yung dot? Pag ginawa nyo lang capital T squared, alright, magrereklamo si MATLAB. Kasi incorrect yung dimension. Kasi tinitreat niya again si T to be a matrix. In our case, T is a what? It's a 1/9 matrix. So T squared is T times T. So you have a 1/9 matrix times a 1/9 matrix that's undefined. Kasi dapat equal yung nasa gitna. Equal yung row number at saka column number noon dalawang pinagmo-multiply natin. So that doesn't work, but if you do t dot square, okay, so t dot caret 2, ito yung bibigyan niya. First entry is 0 squared, second entry is 0.0625 squared, then the third element is 0.125 squared, and so on. Ini-square niya bawat isang element. So, ibig sabihin niya, naka-square na bawat isang element. Pag t dot caret 2 yung exponent, so i-exponentiate niya lang yan. Makukuha ko na yung data d. Right? And then I'll just run this code, right? Interpolation. And here you go. Okay. So ito yung degree 8 algebraic interpolating polynomial relative to the abscissas we have chosen. Right? Double check ko nga kung tama. Hopefully, hindi. Dapat tama siya. Okay, good. This is exactly the polynomial that you see in the module. Right? Tapos ngayon, para ma-approximate yung integral ni e to the x squared dx, etong function na to yung i-integrate ko from 0 to 1/2, right? Tapos ano nga bang syntax ng integral kay MATLAB? So kapag may mga questions na ganyan, before nyo ako i-PM, try nyo munang i-Google kung ano yung syntax. Ano? So halimbawa dito, or kahit nga naka-offline kayo, punta kayo dito sa sa upper right-hand corner. Meron ditong ano man tawag dito? May search box dito. Alright? So type nyo lang ay, halimbawa, okay. So meron siya diyang mga ibibigay. Kaya lang hindi niya ibibigay yung gusto. So, let's see the help ni MATLAB. So, paano ka nag-i-integrate? Hindi niya binigay yung gusto kong command. Kasi ang binibigay niya ng integral, numerical integration na. Pero ang gusto ko kasi ay symbolic. So, symbolic. Tingnan natin sa symbolic. Okay. Pinahiya ako ni MATLAB. Hindi niya nilabas yung gusto kong command. Pero ang command ay int. So, when the MATLAB fails, puntaan na kayo kay Google. So type nyo lang, how to integrate a function exactly in MATLAB. So ibibigay niya sa inyo yung integral command. And the integral command is int. So i-search nyo sa MATLAB, ayan. Int yung syntax, right? Pagpa-compute ng integral, the int command evaluates the definite and indefinite integral for a specific class of functions. Hindi lahat kayang symbolically i-integrate ni MATLAB, pero at least ang kagandahan ng integrate lang naman natin ay polynomial. Kayang-kaya ni MATLAB yan. Alright? And here are the variations for the syntax for int. Ang kailangan kong gamitan na itong pangatlo. May description dito, bawat isa dun sa tatlo na yan. Pero you will see that I want the third one because this syntax will compute the definite integral, which is written first as the first parameter or the first input to int, right? From A to B. Yun yung gusto kong gawin. So balik ako kay MATLAB window. Gusto ko nga yung i-integrate. So doon na lang sa command window mag-work. Kasi na-run ko na yung mahabang command. I don't need to rerun it again. Tapos paulit-ulit gagamitin yung integral command. So dito na lang ako sa calculator. Doon sa command window magpapakompute. So I want to integrate. So I'll use int. Integral ni polynomial p, which is our AIP in this case, and then from 0 to 0.5. And I hit enter, and this is the exact value. Okay, kaya niyang ibigay yung exactong fractional value. But for us, it doesn't make too much sense to use the fractional value kasi nga nag-numerical estimates nga tayo. So kunin natin yung double precision representation nung answer. Okay, and that's 0.5450. Now, if you want to see more digits, punta lang kayo dito sa workspace, tapos si ANS, i-copy nyo yung value, tapos i-paste nyo sa command window, you get a more precise representation. Okay? And this is what you got in the module. So any questions about these things that we did in MATLAB? Wala naman? So I hope nagbe-build na kayo from mula sa mga previous sessions at nagiging mas familiar na kayo how to manipulate MATLAB. Ano? Makikita nyo, napaka-intuitive niya talagang gamitin. Right? Any questions? So sana by the end of the class ay ano, talagang makumbinsi ko na kayo na mag-MATLAB ano, at the end of the semester. Pero yeah. Okay, let's go back to the module and see the remaining topic. This is the last section of module number 2, finally, ano? And it will be about the error in the interpolation. So this is a component of any approximation theory na kapag ka nag-define ka ng isang model para sa isang bagay, or you want to replace a set of data or a function by another function, the natural question is, how good is the approximation? Gaano kaganda yung approximation procedure na ina-apply natin to a certain scenario? And for interpolation, titingnan natin gaano ka-accurate yung ating modeling using the algebraic interpolating polynomial. I laid down the complete theory in section C of module number 2, but sige, dahil masyado pang maaga, i-skip ko siguro yung ilang mga theoretical parts. Ano? For instance, the proof of theorem 2.4, gagamit siya ng generalized Rolle's theorem. But I don't think it is too important for us. Pero sige, reading assignment na lang yung proof ng theorem 2.4. Baka kasi pag pinove ko yan, di ko na naman matatapos. So just do it as a reading assignment. Just for you to appreciate yung paggamit ng Rolle's theorem. Kasi sa Math 36, nakita nyo na dapat si Rolle's theorem. Kaya lang, pinasadahan nyo lang. And you didn't even mind, para saan ba to? Parang pahirap lang naman tong theorem na to eh. Pero makikita nyo sa proof ng theorem 2.4, napaka instrumental ng generalized Rolle's theorem. Kasi itong Rolle's theorem na to, ito yung magbibigay daan sa atin para makakuha na, or para makita gaano kaganda yung approximation. What is the measure of error incurred in the approximation procedure? And remember, in our approximation procedure, we are basically replacing the function f, or a function f, by an algebraic interpolating polynomial, say p sub n of x. All right? Question, how good is this approximation? Para ma-anticipate natin na ano yung range ng possible errors. So at the worst case, gaano kamali yung model natin para masabi natin na confident tayo up to some extent dun sa ating approximation. And if the theoretical error is not to our satisfaction, then maybe we can improve the approximation by doing some things. At yun yung gagawin natin in the remainder of the chapter kung saan i-improve natin itong approximation na to. But before we can do an improvement, or before we can seek an improvement for the approximation, we need to understand how good is the approximation first. Okay? Now, yun nga yung ibibigay ng theorem 2.4. With the aid of the generalized Rolle's theorem, ang sasabihin sa atin, ganito yung error. Una, dapat yung function mo muna n+1 times continuous. So, ibig sabihin, si f, together with its n+1 derivatives, are all continuous. Okay? Tapos, kung si p, yung interpolating polynomial, relative to f, given the abscissas x1 until x sub n+1, so therefore p is a polynomial of degree at most n, sa interval AB, then, sasabihin ng theorem, this is the powerful statement. Kapag ka meron kang x mula dun sa smallest abscissa hanggang dun sa highest abscissa, alright? Yung error ay equal dito. Okay? Or actually, ito lang yung error. Kasi si f, Okay, this is the function that we are approximating is exactly equal. Take note of the use of the symbol equal. So ibig sabihin si f ay eksaktong equal dito. And what does the right-hand side represent? This is the algebraic interpolating polynomial, and actually this guy is our error term. Okay? Bakit siya naging error term? Kasi that will be f of x minus p of x, right? You simply transpose p of x to the other side. This will give us n plus 1 derivative of f, evaluated at some number c, all over n plus 1 factorial times the product na ito. Right? Tawagin ko itong omega of x. So that means indeed, etong part na to, let me highlight it, this is the error term in the approximation or in the interpolation. Kapag ka si f ay n plus 1 times continuous, the error in the approximation is the n plus 1 derivative of f evaluated at some number c, but unfortunately, we don't know what the number c is. This c, which depends on the variable x, or the number at which we are evaluating the interpolating polynomial at, all right? Ang alam lang natin kay c, siya isang number na nandun sa closed interval AB. Pero hindi natin eksaktong alam ano si c. All over n plus 1 factorial times this product. Product ng mga binomials of the form x minus interpolatory abscissa. Now, sir, parang wala namang maitutulong yan kasi hindi natin alam kung ano yung number na c. Or bakit nga ba hindi natin alam yung number c? And actually, if you think about it, it makes sense na hindi natin malalaman kung ano yung number c na gagamitin natin para makuha yung error. Kasi kung alam na natin yung number c, madedefine na, makukompute natin to explicitly, ibig sabihin makukuha ko yung exact value ni f. So why should I use p if I have access to the error term? Ito na yung gagamitin kong pang-approximate kay f. Actually, hindi na siya pang-approximate. Eksakto na itong equal kay f. It's a representation of f. But again, in the real world, we don't know what the exact error is. Because if we have an access to the actual error, i-add ko siya dun sa approximate and that would be the actual value. Yun yung gagamitin ko na sa computations ko. Right? So, mystery, itong number c na to. And usually, kapag ka meron tayong number na involved sa error, na hindi natin kayang i-pinpoint kung ano yung value niya, tatawagin natin siyang c. Alright? So, kailangan nyo itong sauluhin or tandaan by heart itong error term na to kasi this will pop up a lot in the course. So, n plus 1 derivative evaluated at c all over n plus 1 factorial times the polynomial omega. Right? So, si omega ay product lang ng x minus first abscissa times x minus second abscissa all the way up to x minus the n plus 1 subscissa. So, ibig sabihin ito ay degree n plus 1. Ng leading coefficient ay 1. So, this is a monic polynomial of degree n plus 1. Right? So, let's see how this is used. This example. So, medyo mahaba yung proof. That's why I decided not to discuss it right now. Pero, yun nga. Ito yung error term kapag gumagamit tayo ng degree n polynomial. Oh, before we go to a specific example, let's take a closer look at this term, the error term. So, ibig sabihin, ideally, gusto natin itong palitin. We want this to approach 0. Now, do you guys have some ideas? How can we make it go to 0? Any guesses? Anything that comes to mind? How do I make it close to 0? Okay? Kailangan nyo lang tandaan, ito ay constant. Kasi kukomputing ko yung n plus 1 derivative ni f, ipa-plug in ko yung isang constant. Hindi ko alam yung constant na yun, but essentially this is just a number, right? This is a constant. N varies because n plus 1 is the total number of points. And yeah, perfect, Chris, Neil. That's one way to do it. Or at least at the back of our minds, baka yun yung pwede natin gawin. Kasi sabi ni Neil, okay, damihan kaya natin yung points. Bakit kaya nasabi ni Neil na dagdagan yung number of points? I-increase daw si n o i-increase si n plus 1. Why do you think Neil had that idea? Yan, nag-deviate na naman ako sa script ko kaya humahaba yung discussion, eh. Dapat diretso na ako ng example, eh. Pero it's a nice thing to analyze this thing, right? Ganito yung ginagawa kasi sa numerical analysis, eh. Gagawa ka ng isang method, tapos ita-try mo siyang i-improve. Titingnan natin yung weaknesses niya, alright? Okay, Kiran says, oh, yan. Thank you, guys. Marami na nagsabi. Sabi ni Reynald, the higher denominator value will be closer to 0. Yeah, you're right. The bigger the denominator is, the smaller the value is. Sabi ni Kiran, nagiging malaki yung denominator, right? Nasa factorial daw yung denominator, kaya mas malaki yun lalo. Sabi ni Prince, large denominator from Braille, Victor dividing by large number. Medyo mas analytic si Mary. Pero lagay ko muna natin sa quotes yung suggestion ni Mary na limit ng E sub n as n approaches infinity daw ay equal kay 0. Well, let's see about that. Pero that's a nice guess. Siguro yun ay dahil din dun sa suggestions kanya. Hindi yung sinasabi ni Crizel, ni Trisha, at saka ni Rensis. Na, ito yung itsura niya. Kapag ka pinalaki natin si n, kahit ito ay constant lang naman eh, no? So maging constant yan, tataas lang yung order ng derivative, tapos itong n plus 1 factorial, magiging malaki yan. At ang bilis lumaki ng factorial, right? So isa sa mga pinakamabilis na mag-grow na functions yung factorial. So a slight improvement on n can make this much larger. And if you have a larger denominator, the fraction hopefully goes down to 0, right? Pero remember, nagbabago rin to with respect to n. Pero this will essentially be a constant, so I don't think there's a biggie there. Kaya lang natatandaan niyo yung lab exer 1. Anong nangyari nung gumamit na kayo ng mas maraming points doon sa historical price? Di ba unang ginamit nyo ay 7 points doon sa historical price. Tapos, anong nangyari nung dinagdagan nyo yung number of points doon sa historical price? So the suggestion makes sense, right? Yeah, pag tinignan mo yung E sub n, mukhang lumalaki siya, mukhang gaganda yung approximation. Pero tama si Elgin, dun sa exercise, hopefully you recognized na lumayo na yung graph dun sa scatter plot. Sabi ni Axel, ni Kiefer, sabi ni Kiefer, yeah, merong mga outliers. Sumalaki yung relative error kapag ka lumalaki yung number of points. Bakit kaya? Yung analysis natin dito, palakihin lang si n, mukhang liliit yung E sub n. Kaya sabi ko dun sa idea kanina ni Mitzi, lagyan muna natin ng quotes kasi hindi pa laging nagiging totoo yon. Right? Saan kaya nanggaling yung error? So di ba parang nagbe-make sense naman? Pag pinalaki mo si n, liliit ito kasi mabilis lumaki yung n plus 1. Okay? Anong mangyayari pag in-increase ko si n? Kasi ang problema sa analysis natin kanina, ito lang yung kinonsider natin. Right? Pero pag pinalaki natin si n, anong nangyayari? Lumalaki rin yung degree ni omega. Right? So, di ba si omega ay x minus x1, x minus x2, x minus x3, and so on. Alright? Hanggang x minus x sub n plus 1. So, pag pinalaki natin si n, lumalaki yung degree ni omega, posible na maging malaki yung value neto. So kailangan we strike a balance between the value of this guy and the value of omega. Yun yung titingnan natin in modules 3 and 4. Tapos mas i-analyze natin ano yung nangyari, bakit nagkaroon ng outliers pag pinapalaki natin yung number of interpolatory abscissas na na-observe nyo dun sa exercise. Bakit ganun? Parang hindi siya nag-make sense. So yun yung mga titingnan natin in the next 3 modules. But for now, let's play around this error term. Pero those are some things that you can think about. Right? Pero ito yung general theme talaga ng ginagawa natin sa buong sem. Halimbawa, sige, medyo nanganganib na naman ako sa oras. Gusto ko na talagang tapusin itong module number 2. So let's take a look at 2 quick examples. For instance, we want to find the theoretical error bound. Well, basically, ito pala, before I proceed there, okay, the validity of this error bound is from the interval, the interpolatory interval AB, or more precisely, this error term is valid only on starting from the smallest abscissa until the largest abscissa. So outside of the interpolatory interval, we don't know what will happen. So we are not able we don't have any quantification for the error outside the interpolatory interval. Kaya sinabi ko sa inyo dati, magagaranti lang natin na maganda yung error kapag ka nasa loob ka ng interpolatory interval. Pag nasa labas ka na ng interpolatory interval, it's chaos. Hindi natin alam kung gaano kaganda yung approximation. That's why I said na kahit interpolatory polynomial yan, ang domain natin i-consider niya ay from the smallest abscissa hanggang largest abscissa because that's the limitation of theorem 2.4. This is only true for all x's in the interpolatory abscissa. Outside of this, we don't know what happens. Okay? Kaya hindi natin ginagamit ang interpolatory polynomial para mag-forecast ng value. Kasi nga valid lang to from the smallest to the largest abscissa. Pag magpa-plugin ka sa kanya ng value na mas mataas na dun sa highest abscissa, we don't know how the error would how large the error would be. Right? Posibleng napakalaki na ng error, so kasi wala na tayong quantification para sa error na yun. Kaya interpolatory rin ang tawag sa kanya in. Kasi dapat inside the interpolatory interval, yung mga pina-plug in natin dun sa AIP. Iba siya sa extrapolation. Yung extrapolation, pwede kang gumamit ng values outside the extrapolatory interval. So, yun yung mga forecasting techniques. Pero yung interpolation, hindi siya pwede sa forecasting. Okay? Alright. Nag-digress na naman ako ron. Pero anyway, yeah. Tingnan natin yung example 2.7. So, we find the theoretical error bound. Okay? Kasi nga hindi natin alam kung ano yung eksaktong error. But at least theorem 2.4 will give us an idea how big the error could become. All right? So, dahil gusto kong makita gaano kalaki, kasi gusto natin makita yung worst case scenario. Gaano yung pinakamalaking posibleng error. So, ang gagawin ko, kukunin ko yung maximum value or maximum possible value ng error term at a particular number x kung saan ako nag-evaluate. Okay? And yeah, kukunin ko yung pinakamalaking posibleng value niya. For instance here, ano daw yung theoretical error bound kapag ka i-interpolate ko si sine ng 1 using the algebraic interpolating polynomial with the following abscissas. So remember, yung theoretical error, ay ito, ang E sub n ay equal kay n plus 1 derivative ni f evaluated at some number c all over n plus 1 factorial times omega. Si omega ay product ng mga x minus x sabays. So we'll have x minus 0. Ano yung susunod? X minus pi over 2 times x minus pi and x minus 2 pi. So ito yung theoretical error para doon sa approximation problem na to. Pero si f, ano yung ini-interpolate natin? Ang ini-interpolate natin ay sine of 1. So f of x is equal to sine of x. Kasi siya yung siya yung ini-interpolate natin. And then we're using 4 points, so I need to get the fourth derivative of f, right? Because remember, the number of points coincide with the order of the derivative involved in the error term. So kukunin natin yung fourth derivative kasi 4 points yung ginagamit natin, right? And luckily madali lang kasi si sine lang naman yung function natin. Fourth derivative niya ay, anong fourth derivative niya? First derivative ay cosine, second derivative ay negative sine, third derivative negative cosine, fourth derivative ay positive sine, right? So fourth derivative ni sine x ay sine x din. Tapos, kailangan ko siyang i-evaluate. So, kailangan ko i-evaluate yung fourth derivative, which happens to be sine also, kay psi. So, ibig sabihin yung error dapat ay sine ng psi over 4 factorial times, ano yung x value natin? Gusto kong tingnan yung theoretical error kapag kasi x ay equal kay 1. So, ibig sabihin, ito ay magiging 1 minus 0, 1 minus pi over 2, 1 minus pi, 1 minus 2 pi. Alright? Yan yung makukuha kong value. Kaya lang, hindi ko makukuha yung numerical value niyan. Kasi I don't know what psi is. All we know is that psi is a number from the smallest abscissa 0 up to the highest abscissa 2 pi na nakadepende dun sa ina-approximate natin. Alright? Ina-approximate ko si 1, so merong corresponding psi, or sorry, may corresponding c para sa kanya na nanggagaling sa 0 to 2 pi. Kaya lang, there's no way that we can determine what psi is. Existence lamang ni psi yung alam ko. Pero to get the worst case scenario, gaano kalaki yung posibleng maging error, I will get the maximum value nito. So magiging medyo pessimist ako. Kasi gusto ko makita ano yung pinakamalaking posibleng error na makuha ko dun sa interpolation. So kunin ko yung pinakamalaking posibleng value ni sin c. Alam ko lang si c nagsisimula sa 0 to 2 pi. So ibig sabihin, in the worst case, sin of c is equal to 1. So that's why here I get 1, the worst case value or the highest possible value of the n plus 1 derivative of f, right? Over the interpolatory interval, that's 1, divided by 4 factorial times the value of omega evaluated at the given x value na gusto nating i-approximate yung f, right? So that will just be 1 minus 0, 1 minus pi over 2 times 1 minus pi times 1 minus 2 pi. And this is just a constant, all right? Essentially, we'll have this guy, tapos ito. When you evaluate its value, that means kapag ka nag-approximate, o pag i-approximate natin si sin 1 using an interpolating polynomial relative to the abscissa 0, pi over 2 pi, and 2 pi, yung pinakamalaking posibleng error, or in the worst case, yung error ay 0.2690. Alright? Pero alam na natin, hindi na dito lalampas yung error. This is our error bound. Ito na yung pinakamalaking posibleng maging error. So if this is good for you, then that's fine. You use the interpolatory polynomial relative to the 4 abscissas. However, kung hindi yan enough, then you have two options. Number 1, increase the value of n. Because increasing the value of n will hopefully drive the value of this guy down. Kasi doon tayo mag-rely. Sana enough yung paglaki ng denominator para ma-counter kung ano man yung side effect ng pagpapalaki natin kay n. Pero may isa pa kasing paraan. Hindi ito yung ating paglalaruan. Pwede kasing ito yung paglaruan natin. We can choose the abscissas so that this guy will be much smaller than what we have so far. Yun ay kung may option tayo sa pagpili ng abscissas. Bakit kasi 0 pi over 2 pi at saka 2 pi lamang yung gagamitin natin? Baka may mas optimal na abscissas na gamitin na mas liliit itong value nito. Right? So if I get the same number of points, if I still have 4 points, right? So ito ay ganun pa rin ang magiging value, pero posibleng maiba yung error kapag kaiba na yung mga abscissas na pinili ko. At yun yung gagawin natin sa module number 3. Ano yung optimal choice for the abscissas na magpapababa dito sa error term. Right? But that's for later. So any questions about this evaluation? Maximum error? So if you have classes right after this, you guys can go now kasi baka tatakbo pa kayo sa face-to-face class. Pero if you can stay, I'll appreciate it. Siguro tapusin ko yung example 2.8 for 10 minutes, all right? So para saktong 9:30. Tapos if you won't be able to watch it, if you cannot stay, you can just watch it later via the recording. Okay lang ba yun? I hope that's okay. All right. Tingnan natin yung example 2.8. And maybe we can also discuss it via MATLAB para kasi makikita niyo na medyo mahirap pala minsan yung pagkuha ng error bound. Kasi rito, swerte tayo kasi ang tanong ay medyo specific. Ano yung maximum possible error kapag kasi sin 1 ay i-approximate ko using this abscissa? What if I'm asking a more general question? What is the maximum possible error when using the interpolating polynomial over the entire interpolatory interval? Halimbawa, hindi ko lang gusto kay sin 1. Gustong i-evaluate yung error. Gusto ko nang mahanap ano yung pinakamalaking error na pwedeng mangyari sa buong interval AB. Yun yung medyo mahirap na gawin, right? And yun yung pinapakita ng example 2.8. Look at example 2.8 and how it is phrased. Find the theoretical error bound. So titingnan natin ano yung posibleng pinakamalaking error pag nag-interpolate tayo ng sin x using this particular abscissas. This is very similar to example 2.7 except that hindi na tayo binigyan ng specific value ni x. Mas generic yung tanong. Sa buong interval A, B, ano yung pinakamalaking posibleng error na makuha natin? Right? So for this, we just need to find an inequality involving the error term. Okay? Paano to natin nakuha? Well, let's do it step by step. So meron akong e sub n of x, absolute value niya. Ito ay gusto makuha ng upper bound para sa kanya. And the upper bound for it would be the maximum value ng n plus 1 derivative ni f evaluated at c all over n plus 1 factorial naka-absolute value times omega of x. Right? Pero alam na natin si f ay sin x. Tapos ang n natin dito ay 3 kasi meron tayong 4 points. N plus 1 is 4. So n is equal to 3. Tapos alam na natin ang fourth derivative ni f. Sige na nga, palitan ko na to ng 4 para mas clear yung solution. So fourth derivative, 4 factorial. So we already know what the worst case scenario here. So kukunin ko yung maximum x coming from AB. Kasi nga gusto ko ng error bound. So buong AB, ganito yung pinakamalaking posibleng error. We're good because here we know that this guy has maximum value 1. Then we have a 4 factorial below. So pwede na natin itong ilabas as a constant out of the maximum. So this would be 1 over 4 factorial. Ang matitira na lang sa loob ng max ay si AB. Si AB. Max kay AB ni omega. Pero ano nga ba si omega? Si omega ay x minus 0 times x minus pi over 2 times x minus pi times x minus 2 pi. Okay? Tapos ito ay maximization problem. Kailangan nating makuha ano yung maximum value niya. Sabi nung example ko, ang maximum value niyan ay 42.09. Of course, it's hard to compute it by hand, so gagamitin natin si MATLAB. So take note, we are maximizing omega. All right? So gawin natin siya kay MATLAB. Pakita ko kung paano siya gagawin. Pero nakita na natin to last time, di ba? Kung paano nag-maximize ng isang function. Gagamit lang tayo ng critical numbers then first derivative test. Okay? Let me just demo it a bit para along these lines yung gagawin kong exercise on Monday. So let me stop sharing my PDF and let me shift to MATLAB. Okay? Right. Sulat ako ng isang maikling script. Hold on. Ulitin ko yung share screen. Di yata na share. Okay, so I hope you have my screen right now. Okay, so ngayon, i-clear ko muna yung workspace para walang problema. Hindi magamit yung mga clear para mawala silang lahat. Kung marami kang figures na naka-on, type close all doon sa command window, mag-close lahat ng figures para hindi makakain ng RAM. I-program ko si omega. Sulat ko yung pagko-compute kay omega. So, I'll first define x to be a sim nga ba o sims? Lagi ako nalilito dyan. Sims yung gagamitin. So, sims of x, para lang masabi kay MATLAB na symbolic variable si x. Tapos, si omega ay product ng mga binomials. So, I need to initialize the value of omega to 1. And I'll put a semicolon para hindi niya i-display yung omega equals 1. Then, I'll have a for loop here. Ilan nga yung meron tayo? 4. Tapos N4. Okay? N ko yung for loop. Kasi 4 yung points na ginagamit natin. Siguro, i-type ko na rito si T. Si T nga pala ay 0 pi over 2. So yung value ni pi, just type pi para sa pi. Pero small letters sila dapat. Tapos pi. Tapos 2 times pi. So ito yung mga abscissas natin. Kailangan ko siya para kay omega. Tapos siguro to make it more general here, I'll do the for loop from 1 until the length of t. Kasi kung ito si t, so run natin itong t. I'll hit F9 para lumabas sa workspace si t. Yung length ni t ay equal kay 4. So this will do it from 1 to 4 para i-automate niya. Hindi nyo na kailangan bilangin ilan si t. So input nyo si t, tapos dito gawin nyo yung for loop from 1 until the length of t. Tapos saan to equal? This will be omega equal to the previous value of omega times x minus the ith abscissa. So this would be x minus t of I. Oops. So ganito natin binubuo yung omega. Remember, omega is the product ng mga x minus x sub I. So I start with omega equals 1. Then equal to 1, we will have omega, which is 1, times x minus the first abscissa. Tapos papasok siya sa for loop. So meron ka ng x minus first abscissa. Pero yung omega na yon, i-multiply natin by x minus the second abscissa. And we do the process over and over again hanggang si omega maging product na nung lahat ng apat na abscissa. So, pwede natin itong i-save, pero ayoko siyang i-save. Control A na lang ako. Tapos right-click, evaluate selection. And if you want to see how omega looks like, here it is. So, ito na yung gusto nating mangyari, right? X minus, x times x minus pi times x minus 2 pi times x minus pi over 2 as we have in the module. All right? Kaya lang gusto ko itong i-maximize. So gusto kong i-maximize si omega. So parang gagawin ko yung ginawa natin dun sa commodity problem natin last time. So una, kailangan ko munang computein yung derivative ni omega, right? Para makuha yung critical numbers. So I'll create a variable named omega prime. Sabihin ko, ito yung derivative ni omega. Okay. Alright, para ma-compute yung derivative ni omega. Tapos, kukunin ko yung roots ng derivative ni omega o yung yung roots ni omega prime. Pero para mapagawa yung kay MATLAB, kailangan ko ng coefficients, right? Kailangan kong i-harvest yung coefficients ni omega prime. So, gawin natin itong coef equals sim to poly ng omega prime. Right? So, ang sagot dito sa coef ay isang vector na laman niya yung mga coefficients ni omega prime. Kasi yun lang yung tinatanggap ng roots command. So, yung critical numbers ko ay equal kay roots ng coef. Ibibigay niya yung mga critical numbers. Alright? Tapos, hindi naman lahat ng critical numbers ni omega ay gusto ko. Gusto ko lamang ay mga critical numbers from the smallest abscissa to the largest abscissa. So, kailangan kong i-filter ngayon si Cn para ang laman niya lang ay mga critical numbers na nasa loob ng interpolatory interval. Na madali lang to rito kasi kung gagawin ko siya rito, so run ko to, titingnan ko si Cn. Si Cn, tatlo lang yung laman. Understandably so because omega is degree 4. So ang omega prime ay degree 3. So sabi ng fundamental theorem of algebra, meron tayong at most 3 roots. At ito nga yung tatlong roots ni omega prime. Tapos madaling i-check kung sino sa kanila yung critical numbers within the interpolatory interval, right? Pero kung halimbawa 100 yung critical numbers nyo, kailangan yung i-filter sino lang yung nasa loob ng interpolatory interval because we don't care what happens outside the interpolatory interval, right? So para ma-filter yung isang vector, right? So type nyo lang yung vector, Cn, i-overwrite ko siya ngayon. I-overwrite ko siya ng mga elements ni Cn pa rin, pero dapat yung value ni Cn ay mas malaki sa smallest abscissa and dapat siya ay mas maliit sa pinakamalaking abscissa. So this line will just give me a filtered vector Cn. So paano mag-filter kay MATLAB? Pangalan, filter, tapos nasa loob niya kung ano yung condition. Nakita niyo yung condition na to, dapat kukunin ko lang yung mga entries ni Cn na greater than or equal sa minimum t and dapat mas maliit dun sa maximum ni t. So para matanggal na natin kay Cn yung mga critical numbers outside of the interpolatory interval. Right? So let's see what happens now. So run ko itong Cn command na to. Tapos type ko ulit si Cn. Okay, tatlo pa rin yung binigay niya kasi itong tatlo na to ay within the interpolatory interval. Tapos kukunin na lang natin alin sa kanilang tatlo plus dun sa endpoints yung may pinakamalaking function value. Right? So pwede kong ipagawa double ng subs kay omega. Kaya kanino ko siya i-plug in? Kay omega, no? Kasi gusto nating makita ano yung maximum value ni omega kay Cn. Okay. So ito yung values ni omega doon sa tatlong critical numbers na nandun sa interpolatory interval. Pero sabi nga, may nakalimutan plug in yung 0 at saka si 2 pi yung endpoints ng interpolatory interval doon sa kay omega. Para makita ko talaga ano yung maximum ng omega from 0 to 2 pi. Palakihan lang naman to ng values, no? Nag-0 lang naman sa endpoints, that's fine. So ito na lang yung titingnan ko. Actually, magzi-0 pala siya talaga kasi x minus 0 at saka x minus 2 pi ay factored ni omega. So pwede na natin i-skip yung part na yun kasi si omega nagzi-0 sa lahat ng interpolatory interval. So at this point, I know that the maximum value or the maximum absolute value of omega is negative 42.09, is positive 42.0935. Kasi naka-absolute value, remember, yung kinocompute natin. All right? And that's how I got yung nandun sa handout o nandun sa module na multiply na maximum value ni omega. Right? Kaya ako nakuha itong 42.09. Delayed yung aking share niya. This is how I got it. Right? That's the maximum value of omega on the interval 0 to 2 pi. Divide ko lang by 24 para makuha ito. So ito yung sagot. Ibig sabihin, pag nag-plug in ako ng isang x dun sa interpolatory polynomial or sa AIP, ang maximum error ay 1.75. The maximum absolute error ay 1.75, which is huge. Kasi bakit ito malaki? Kasi ang maximum value lang ni sin ay 1. Ang maximum error ay 1.75. So, ito yung worst case na dapat bantayan. Pero hindi ibig sabihin na nahi-hit itong maximum na to. The error could be much more less than the error bound. Because what we are just claiming here is that the error will not exceed 1.75. It could be much, much less than 1.75, pero hindi na siya lalampas ng 1.75. Now, if you want to get a more precise estimate of how good your approximation is, i-plot natin si sin x at saka yung interpolatory interval. You see na halos magkamukha lang sila, medyo masyadong pessimistic lang yung error bound. Ang sabi natin, yung maximum error ay at most 1.75, right? 1.75 nga ba? Yes, 1.75, 38, and so on. So hindi lalampas yung error ng 1.75, but the approximation actually is much better than that. Medyo medyo masyadong negative. Masyadong nega yung estimate na nakuha natin kasi tingnan niyo yung dalawang curves. Medyo magkamukha naman sila. Although with some delay, pero yung difference ay hindi naman nagkakalayo. Right? It's much less than 1.75. So in that case, we need a tighter bound, pero at least alam natin yung worst case. Hindi siya lalampas ng 1.75. All right? I think I will end here. Sorry, overtime na ako ng 5 minutes. At least finally, we have finished module number 2. So do you guys have any questions? Again, medyo madidelay yung pag-upload ko ng LabXer for Monday. Siguro right before midnight ko siya i-upload later, pag-isipan ko pa. And then I'll need to consult your lab instructors kung okay siya. Pero expect na error analysis yung gagawin natin. So, baka ipagamit ko si Theorem 2.4 para ma-approximate yung error dito. Okay? Yun yung pwedeng mangyari. So, yung pag-approximate ng e to the x squared, paano yung mangyayaring error? Kasi rito, ang error term dito ay hindi na lang yung f. Sige, sa Monday na. Siguro ipapadiscuss ko ng konti dun sa lab instructors niyo, alright? Pero, yeah. Pero maybe something related to this example yung gagawin. Neil has a question, but 1 po ulit yung f to the power 4, fourth derivative ni f. Kasi Neil, dito ay kailangan ko to. N plus 1 yung maximum ng n plus 1 derivative ni f evaluated at x. Kunin ko yung max niya. Si f natin ay sin x. Yun yung given function na gusto nating approximate. Kunin mo yung fourth derivative niya, equal to pa rin kay sin x. And nasa loob siya ng maximum. So kukunin ko yung maximum ng absolute value ng fourth derivative. Ang maximum value ni sin ay equal kay 1. Kaya yun ay napalitan lamang ng 1. So kung mas komplikado si f, mahirap din computein itong n plus 1 derivative. Kailangan nyo ng upper bound para dun sa n plus 1 derivative. Okay? But I hope that answers your questions. So pag halimbawa, binigyan ko kayo ng e to the x, tapos 50 abscisas yung pinagamit ko sa inyo. So kailangan yung kunin yung 50th derivative ni e to the x, tapos kukunin nyo yung maximum ng 50th derivative ni e to the x dun sa interpolatory interval. Madali lang yun kung e to the x kasi ang derivative niya lang naman ay sarili niya forever. So the sad tale of e to the x, wala na siyang iba nakakasalamuha kasi ang derivative niya ay sarili niya lang. 50th derivative niya ay e to the x. Kung ima-maximum nyo to from say 0 to 100, increasing lang naman si e to the x. So ang maximum niya ay e to the 100. Yun yung pampalit nyo dito. Right? So e to the 100 over 100 factorial times omega. Right? Other questions or concerns? So if there are none, thank you guys for joining me today. Enjoy the rest of the day. Enjoy the weekend. We'll see each other again on Wednesday, pero prepare for the lab exercise on Monday. Oh, by the way, before I forget, I don't know kung nag-start na mag-check yung mga lab instructors nyo ng lab exer 1. But what I'll do is I'll upload an answer key. All right? So mag-upload na lang ng answer key. Isang version lang yung ginawa kong answer key. Upload ko mamaya after nung class ko. Or siguro mamaya na rin, right before midnight. I-upload ko, gagawa ko ng page kay Canvas for the answer keys. But my only request is that you access the answer key ng mga exercises na nasubmit nyo na. Alright? Pag hindi nyo pa nasasubmit, huwag kayong mag-tempt na buksan yung answer key na page. And then you can download it for yourself as long as you have submitted the exercise, but don't share it. Kasi lalagyan ko siya ng declaration na by accessing this page, I certify upon my honor that I have submitted the requirement. Alright? So kaya kanya-kanya kayong download, no? Kasi kanya-kanya kayong mag-click-click at manunumpa na na-submit nyo na yung requirement. Alright? Para lang hindi ma-pressure yung mga lab instructors nyo na matapos checkan. Marami rin silang ginagawa. Pero at the same time, ayoko namang ma-short change kayo na hindi immediate yung feedback. So at least you will see my version of the solution and compare it with what you had. All right? Okay, I think that's all. Super overtime na ako. Sorry about that, guys, but thank you for bearing with me. See you on Wednesday. Bye, guys.